This evening we're very privileged because we've got one of the not only Australian but world-renowned experts in a particular field, which is the field of, I don't know, hearing augmentation, or, Dr. Peter Blamey. Peter has a PhD in physics and began working on hearing when he became a member of Graham Clark's cochlear implant research team in 1979, and that was quite early in the piece for that group. He is a co-author of over 200 papers on hearing, sound processing, speech and language, particularly of children with impaired hearing, and also papers on psychophysics, which is probably a topic in itself. He is the inventor of 25 patent families, not patents, patent families for hearing aids, bionic ears and bionic eyes. He's been instrumental in the spin-off and incubation of 4 companies from the Bionics Institute since the year 2000, including Dynamic Hearing, which has provided advanced signal processing technology in many millions of hearing aid platforms and hearing aids globally. Peter is an executive director and co-owner of Blamey Saunders Hears, a company addressing the poor penetration of hearing aid market in order to reduce the $12 billion annual burden of hearing loss in Australia. Tonight, Peter is going to talk to us about technologies for hearing and listening. The talk will cover underlying technologies that have driven a revolution in hearing and listening, driven by Peter and his team, the benefits they bring to users of hearing aids and how they affect the listening experience. And I think there might be a little bit of technical stuff in there too. Okay, well, I'd like you all to give a warm welcome to Peter, and I look forward to hearing you.
Okay, well, it's a pleasure to be here, and thank you for such a warm welcome, Graham. I wasn't quite sure where to pitch this talk, so I hope there's something for everybody, and I hope there aren't too many bits that individuals will find boring. Describing sound processing technologies to lay audiences is something that I had to learn how to do in about 2000 when Elaine Saunders and I found ourselves as the CEO and the CTO of a new company called Dynamic Hearing, and trying to get the big hearing aid companies of the world interested in using some new technology that we'd developed here in Melbourne. So I think I've learned a few things in the last 15 years, but I'm not sure whether they're the right things for this audience, but we'll find out. So the problem that we're trying to solve is this, that people who have even a mild hearing loss start to lose the soft parts of sound, soft parts of speech. So a mild hearing loss is anything from 20 to 40 decibels of hearing loss relative to normal hearing across the frequency range. And you can see from these curvy lines on here that mild hearing loss, if you have a hearing loss on this line here, then you're missing out on about half of the speech information. So even though it might be described by your audiologist or by somebody else as a mild hearing loss, you actually will do better if you can make sounds louder and get more of that speech information into your hearing range. By the time you have a severe hearing loss, you're hearing virtually nothing at conversational levels, and everybody will get very tired of shouting at you just so that you can hear. So that's why there's this rather surprising number that Graham mentioned, that the health economists have estimated that the burden of hearing loss in Australia is about $12 billion per year through lost productivity, through special care for people with hearing loss, through the provision of expensive devices like cochlear implants and hearing aids and so on. I found that a very surprising number when I first heard it, but I think it's relatively easy to justify that number. Now, people have known about hearing loss and have tried to do something about it for a large number of years. And this is probably the first custom hearing device that has been recorded. And it's a chair with hollow arms and a sort of ear trumpet built into the arms. It was actually the throne for King Goa of Portugal, and he had a tube that was connected to these ear trumpets built into the arm that went up to his ear, so that he could actually hear people when they knelt down in front of him and spoke into the arm of his chair. And this device still exists, but ear trumpets have been used in many, many ways since then. This device was designed to be used at the dinner table, so people talking from all directions would, their voices would be picked up in the ear trumpets in the middle of the table, and that tube that's curled around it would go to the owner of the table's ear. And this type of device was still used in the early 1900s, about 1926 or so. This particular picture shows a modern version of that device. Ear trumpets have been used for a long, long time. These were Beethoven's hearing aids. People tried to make them not so noticeable, even in the early days, so tried to make them look like decorations rather than hearing devices. This is a more modern picture. This is a particularly innovative ear trumpet built into a walking stick from 1926. People tried to use large ear trumpets to detect enemy aircraft in World War I before they had radar. This is a very modern device from a university in Germany. I think it's used mostly for teaching students, but it's a rather impressive device. A bit hard to walk around with. And then around about the 1930s or late 1920s, people started making electronic devices. And I was quite surprised to see a modern paper around about 2000 comparing the results of hearing aids to ear trumpets. And the ear trumpets did very well. There are not very many hearing aids in around about 2000 that actually worked better than an ear trumpet. So there's been about 60 or 70 years of development between 1935 and the year 2000, and still we're only just approaching the benefits of an ear trumpet. This person, Michael Hutchinson, developed a thing called the Akoulation, which was the first portable electronic hearing aid. And this is some of his marketing material from about 1901, and it was on the market for about $60 US at that time. Then this developed into a whole lot of other similar sorts of devices. Usually they had a battery pack or a bit of processing with the amplifier in it in a box that was worn on the body somewhere, and fairly large transducers to pick up the sound and to deliver it to the ear. This is an electronic desktop device, and this was used in schools for the deaf quite widely, with the deaf children clustered around this device. The National Health Service started to develop their own hearing aids around about the 1950s, and they looked something like this. And this was the first fully transistorised hearing aid in 1953. So they got smaller over that time, even if they didn't appear to work much better. Ladies and gentlemen used to like to hide their hearing aids, and one of the biggest problems that audiologists faced for about 50 years in the second half of the 20th century was that they got clogged up with talcum powder. So people would put their hearing aid on first before the talcum powder. Then people started thinking about behind-the-ear devices. They were still connected to a large battery pack, but they started to sit up here behind the ear. And one of the advantages of that is that the microphone is in a much better place than on the chest down here, in order to be directed in the right way and to be at the right level, closer to somebody speaking to you. Round about this time in the 1980s, hearing aids started to look a lot more like what they look like today. And this is a modern hearing aid. I like this particular picture because it shows the insides of the hearing aid, which are the most interesting part, really, if you're an engineer or a technical person. And this is a digital hearing aid. So it's got a tiny little computer inside that case. The actual size of the case is about this size, and also inside is a battery that keeps this little computer running for a week. And that in itself is one of the real triumphs of the electronic engineering that makes hearing aids possible. Hearing aids come in several different types. So there are the behind the ear, BTEs. There are devices that are now called open fit devices, which means that instead of blocking up the ear with an ear mould, you actually have a tube that conveys the sound into the ear, but the ear is still open. So there's still sound coming in from the outside, and there's also sound escaping from the hearing aid tube itself. And some hearing aids actually have the speaker device in the ear as well. And about 15 years ago or so, the most popular type of hearing aid was an in-the-ear device. So a hearing aid that was completely inside the ear canal or inside the outer part of the concha as well. And those devices were popular because people thought they were less obvious and harder to see. So one of the things that has driven hearing aid development is people's reluctance to admit that they've got a hearing loss, and the fact that they feel that they're going to be treated as a person who's slightly disabled by the rest of the population. So quite a lot of effort has gone into trying to educate people into thinking that actually it's better to be seen to be wearing a hearing aid than to have people think that you're not listening to them or you haven't understood what they've said, and you give rather strange answers when they ask you questions. So personally, I'd rather be thought to be hearing impaired rather than a bit stupid, but I might actually be in the minority, I don't know. Okay, so this little computer in the hearing aid, what does it do? And I'm sure all of you could give a good answer to this. It actually does quite a lot of things. So the first thing it needs to do really is take the microphone signal and convert it into numbers that it can manipulate with an analog to digital converter. And at the output, it needs to turn it back into an analog signal that can be used by the receiver or the output, the speaker. I have no idea why hearing aid engineers call the output the receiver, but it is common parlance throughout the hearing aid industry. So the analog to digital conversion and the digital to analog conversion actually take time. They don't happen instantaneously, and they introduce together something like a millisecond of delay into this processing path. But the computer itself, the DSP system, typically introduces more of a delay than that. And that was one of the big differences between digital hearing aids and analog hearing aids, where there was very little delay between the input and the output. And that you'll see why that's important a little bit later on in the talk. So this particular device, the Ezairo 7100, is one of the most recent hearing aid chips. This one is made by, it's an open platform device, so it's open to anybody who wants to do a bit of digital signal processing in a very power efficient way. This device has the capacity to run at about 15,000 MIPS or something like that off this tiny battery for a week. And it has an 18-bit analog to digital converter and digital to analog converter at the output as well. And the number of bits in your A to D and D to A is really important, because the range of sounds that people want to listen to is something like 90 decibels or so. And if you work out how many bits you need to do that, then you find that 17 or 18 is pretty close to what you need if you want to have any resolution at all at the lowest intensities. And so you need good microphones, you need good analog to digital converters, you need tiny little speakers, and basically you need excellent engineering to make this thing work. And it's that engineering that has sometime in the last 15 years meant that hearing aids are now better than ear trumpets, and I'm very pleased to say that they are. They can do things that you can't do with an ear trumpet. So I've talked about most of these bits. There are a few manufacturers around the world for the chips, for the microphones, for the receivers and so on. And so if you want to make a new hearing aid, you don't go out and develop a new microphone or a new receiver or a new chip. You actually just buy all those bits, and you spend most of your time working on the algorithms that run in the digital signal processor. So it's these algorithms and the digital signal processor that enables rapid product development and early validation of these sorts of things. So in 1999, one of the technologies that I was working on was an amplifier that was designed to be used for people who had a cochlear implant in one ear and a hearing aid in the other. And the goal there was to make the sounds in the two ears about equally loud across a very wide range of input levels, which is rather difficult because the range of stimulation in a cochlear implant is only about 6 to 10 decibels of electric current, and so there's a huge reduction in the dynamic range of signal that you can apply. And the hearing aid algorithms that were around at the time also had rather unpredictable loudness. So most of the time, people in this situation would be listening to one ear at a time, and just to make it worse, they had two audiologists. They had a left ear audiologist and a right ear audiologist, because neither of the audiologists could program the other device. And so the poor patients using these things really had a terrible time. As sounds changed in intensity and frequency, they would appear to move around in space because of the different loudnesses that were being experienced. Anyway, digital signal processors gave us an opportunity to change this sort of thing, and the amplifier that I'm talking about is the box that's labelled ADRO over there. It stands for Adaptive Dynamic Range Optimization, and that's one of the things that I'm going to talk about today. This is a block diagram of the processing in a fairly modern hearing aid, and you can see there are lots of bits. They all interact with one another in a fairly complex way, and one of the big advantages that the company that Elaine Saunders and I founded in around about 2000 had was that we developed a very modular software architecture for these devices, so that we could change one of these boxes without needing to change all of the others. But the big hearing aid companies around the world who had purpose-made chips to do these sorts of things couldn't change anything without making a new chip and developing a whole new fitting rationale and a whole new way of getting things to work. So every time a new algorithm came along, they were looking at a $10 to $15 million price tag to make a new chip that could do that. Whereas if you went with the open platform devices, you could just write a new piece of software, and it really only cost $100,000 or so per algorithm, for the first one anyway. So something else that we did that was a bit different was that we introduced 64 to 128 channels. So the first hearing aid that we made had 64 channels, and at that time the next highest number of channels in a commercial hearing aid was only about 8, and most of them only had 1 or 2. So part of my job as the Chief Technology Officer was to be able to explain to people why it was a good idea to have 64 when most of the hearing aid engineers around the world said it'll never work. How can you get something to work with 64 channels when they're all interacting with one another and they're all changing at once? You know, it's going to be uncontrollable. But so the first thing we did with our 64 channel device was do a clinical trial and showed that it actually worked better than an 8 channel top of the range hearing aid that was commercially available. And we were lucky enough to find a hearing aid that used one of these open platform chips. So we actually took the same hearing aid, replaced the digital signal processing, and showed that we could make it work better. So there was no chance that it was anything else except the algorithms running in the chip. Okay, so I'm going to talk a little bit more about that amplifier and the clinical trials. This is a sort of visual analogue for what happens. So if you consider this picture to have frequency across the bottom and amplitude along the up the vertical axis, then if you go deaf, you typically lose the bottom part and you can only hear the louder sounds or see the top part of the picture. The comfortable level doesn't move very much, but the threshold comes up quite a long way. So to compensate for this, most hearing aids in the year 2000, and still most hearing aids today, use an algorithm called compression. And this is what it does. So if you're an audio engineer and you imagine what happens when you squash 100 dB of sound into a 50 dB output range, and imagine what it sounds like, you'll know that it's a pretty terrible amplifier. You wouldn't want to use it on your hi-fi because what it's doing is it's distorting all the time in order to make sounds more audible. And people with impaired hearing get used to this, but it does take some getting used to because it's not a natural sound. So what we decided to do instead was this. And so we used a much more linear amplification, and we didn't worry too much about the top end of the dynamic range or the bottom end. We tried to choose the part that carried the most information, and we did that in a dynamic way by making statistical analyses of the sound in each one of these 64 channels. So we found the 90th percentile and we put that close to the comfortable level, and we found the 30th percentile and we amplified things so that that was above the audible level. And if you do that with typical sounds, say a speech sound at conversational levels, for example, there's really only 15 to 20 dB between the 30th percentile and the 90th percentile. So there's plenty of space in the listener's dynamic range to present those signals as long as you choose the right part of the dynamic range. So now I'm going to do a bit of marketing, and this is one of the videos that we produced to explain
My
this.
audiologist. And my audiologist says I hear better with ADRO and my aids because it does this rather than this.
This scene represents the full picture of hearing, a normal hearing person's dynamic range of hearing with access to all sounds from soft to loud. A person with a hearing loss has increased thresholds, so they can only hear the loudest sounds and will lose part of the picture, possibly parts with important information. A hearing aid has to represent the world of sound in this reduced range. Compression has been used for many years to do this. This method compresses the entire picture into the dynamic range of the listener, but introduces distortion. ADRO, however, optimizes the sound to place the most important part of the picture into the dynamic range without distortion. It makes soft sounds loud enough, but always keeps hearing comfortable.
These hearing aids have got a small computer inside, acting like an automatic graphic equalizer with lots of channels, so that each individual one tunes up automatically for all the sounds I like to hear.
The incoming sound is picked up by the microphone and split up into many narrow frequency bands. ADRO acts like an automatic graphic equalizer at each frequency. If sounds are too loud, it makes them softer. If sounds are too soft, it makes them louder. Otherwise, it leaves the natural qualities of the sound unchanged. ADRO amplification optimizes every sound for the individual listener in any listening environment, for the ultimate in mobility.
Okay, so it worked really well. This clinical trial that we did showed that, as shown in the graphs over there, the ADRO amplifier compared to the wide dynamic range compression amplifier performed better at low levels, mid levels and normal levels. And these are results for people, about 20 volunteers who wore these hearing aids for a few months before they did this test. And the hearing aid could switch between the wide dynamic range compression and the ADRO sound processing in the same hearing aid. And it turned out that about 3/4 of these people actually preferred the sound of the ADRO amplifier, even though they had all, or nearly all, been using compression for many years before. And one of the things that happens with people with hearing aids is that they get used to the sound of their hearing aid and are quite reluctant to change. So this was fantastic that we had a 3-to-1 preference for something that was completely new. Just to explain how important this is, these circles around the teacher in this picture show you the distances at which the teacher's voice is normal, in a mid-range and at a low range. So these children over here, if they have a mild hearing loss, are really only understanding about half of what the teacher's saying, even if they've got their hearing aids on. So it's really important for people in that position to get as much amplification as they can. So we thought we were onto a good thing, and we licensed the technology to a small French company called Hutchinson, who unfortunately expanded a bit too fast and went broke about 6 months after we licensed to them, and the CEO ran off to Italy with his secretary. But the other people who worked for Hutchinson all started little companies themselves, and they became very good ADRO customers. So they had a hearing aid which they called the Transparence, for obvious reasons, because the sound was so natural. It was like the hearing aid was transparent. And they sold quite a lot of them. In fact, I think they made a lot more money than poor old Mr. Frickaday, who ran away. But we also discovered that an amplifier doesn't make a hearing aid. People have all sorts of other problems in listening, and listening in background noise is one of the most commonly reported problems. And so once we had a digital signal processor, we could start to do things like develop directional microphones and adaptive directional microphones. So instead of making a physical directional microphone and sticking it on the hearing aid, we could now have a microphone that was omnidirectional part of the time and directional part of the time when it got noisy, and give people the benefit of all around surround sound when they wanted it, and the ability to concentrate on what was going on in front of them when it got noisy. And with just two microphones, if you combine the signals from two omnidirectional microphones, you can get a whole range of different polar patterns. And which one is best depends a lot on the situation in which you are. So it's really important to have an adaptive system. And the system that we developed is designed to keep the signal level from the front, that's at the 0 azimuth at the top, constant, and to, while keeping that input constant, reduce the total signal, the total amount of sound coming in to this pair of microphones to a minimum. So this is on the assumption that what you want to listen to what's in front and reduce everything else to as low a level as you can. And it worked rather well.
Dynamic hearing has shown the benefits of ADRO technology in hearing aids. This has made conversations much easier to understand and more comfortable to listen to. But what about situations where there's a competing sound coming from behind the listener? Dynamic hearing has now developed an adaptive microphone that enhances the sounds you want to hear. In all the demonstrations, we're recording the actual sound as it would be heard by the person with the hearing aid.
Susan's wearing a real hearing aid that's been programmed with Dynamic Hearing's ADRO technology and has selectable microphones. This is the microphone on top of the behind-the-ear hearing aid. The output from the hearing aid is being recorded in this real ear simulator on Susan's shoulder. The signal is going to this computer and being recorded in real time. The computer is also recording the polar pattern of the microphone as it changes. In the corner of your screen, you'll see the polar pattern changing as you're listening to the sound from the hearing aid.
Let's look at a common situation with noise moving behind Susan. Here's how Marty sounds to Susan with an omnidirectional microphone, which picks up sounds equally from all directions.
So you're trying out some new microphones for hearing aids?
Yes, I am.
What sort of microphone have you got at the moment?
An omnidirectional microphone.
Oh. Lawnmower's pretty loud, isn't it?
Yeah.
Can you still hear what I'm saying, or are you having trouble understanding what I'm saying with the lawnmower?
Sorry, I can't hear you. What did you say?
Just ask whether you can hear me or you're having trouble understanding what I'm saying. Because that lawnmower is particularly loud, I would have thought it.
This is how Marty sounds to Susan through a fixed directional microphone, which reduces sound optimally from one direction.
I've switched to a fixed directional microphone now.
Lawnmower's pretty loud, isn't it?
Yeah.
Can you hear me well, or are you having trouble understanding what I'm saying?
It's better now, but can you say that again?
Now let's have a listen to how Marty sounds to Susan through the automatic adaptive microphone, which always chooses the best microphone configuration for the listener.
I've switched to my adaptive microphone now.
Sorry, I'm having trouble hearing you. The lawnmower's pretty loud, isn't it?
Yeah, but not as loud as before.
Well, that's good. So you can hear me better now?
I can hear you pretty well, actually.
Oh, that's great. It must make a big difference for you.
Yeah, it does. And it doesn't matter where the lawnmower is.
Right. Well, that's great.
I'm finished. I hope I didn't disturb you too much.
No, that's fine with this adaptive microphone.
The adaptive directional microphone works well in a diffuse noise source as well, like a garden party. Here's how Marty sounds to Susan when her hearing aid is switched to the omnidirectional microphone.
Pretty fun party you got going on.
It's a pretty good turnout. It does make it hard to hear though, with everyone talking at once.
What's a microphone does, mate?
An omnidirectional microphone.
Direction, so you can get all the sound from every direction.
Yeah.
Now, let's listen to Marty when Susan's hearing aid is switched to the adaptive microphone.
I just switched to my adaptive microphone. I was finding it too difficult to hear you before with everyone else speaking at once.
Are you able to hear me clearly now?
I can hear you pretty well actually.
Good, that's great, because I'd much rather you be able to understand what I'm saying to you.
Yeah,
Clearly,
well,
the
that
quality
makes
of the sound that Susan can hear with an adaptive microphone that adjusts to the sounds behind her is much better in both situations.
Well, that's good. So you can hear me better now?
I can hear you pretty well actually.
Okay, so using two microphones and making them adaptive produces an obvious big benefit in noise. And we call this an automatic microphone. It becomes directional as sounds get louder. So most of the time it's omnidirectional, and as sounds get louder it starts to kick in with a directional signal. Now, I actually wear hearing aids like this in noisy situations, and they help me hear better. So this directionality benefit doesn't depend on the degree of hearing loss that you have. So even if you've got good hearing, you can get a substantial benefit by wearing a hearing aid with an adaptive directional microphone. And you may have seen in the news and other places that there are claims that these sorts of hearing aids actually help people hear better than normal. And that's true in some situations, not every situation. So the benefit depends on which direction the sound is coming from, and the benefit is actually biggest when the noise is behind and you're listening to a sound that you want to hear from the front. In the other directions, the separation between the sound from the front and the noise is actually quite good without wearing any hearing aids, because of the head shadow effect. So if the sound's coming from over there, then you've actually got a pretty good signal to noise ratio in this ear. And if the sound is coming from over there or over there, still this ear is a lot better, and the brain is really good at picking out the ear with the better signal to noise ratio and listening to that one. That's one of the reasons why the title of this talk is not just about hearing, it's about listening as well. If you don't take into account what the brain is doing with these two signals that are coming into the two ears, then you end up with a quite wrong impression of the amount of benefit that you might get by doing particular things. When people come into our hearing aid clinic, we give them a test with speech from the front and noise from behind, with and without hearing aids, and we can usually demonstrate a 7 or 8 dB advantage when you're wearing hearing aids, regardless of what the person's hearing is like. Directional microphones are also good in reverberative rooms. So if you're in a room talking at a normal sort of level and the reverberant noise is just bouncing off the walls, if you're more than about a metre and a bit away from the speaker, then the reverberant signal is just as loud as the speaker, as the direct signal, and so you've actually got a reduced signal to noise ratio. If you've got a directional microphone, that shifts out to about 2.5 metres, and so that's enough to stretch across a table in a restaurant, for example, so that you can actually hear the person on the other side with a positive signal to noise ratio compared to the reverberation in the room. Okay, I want to move on and talk a bit more about signal delay. How am I doing for time? What time do you expect me to finish?
We'll give you a 10-minute warning.
10-minute warning, okay, good. So with these open fit devices that I mentioned briefly before, we've got sound coming into the ear, and we've got the amplified sound being applied to the ear as well. And there's a delay of at least a millisecond because of the analog to digital conversion and digital to analog conversion, but there's also a delay because of the sound processing. And some hearing aids in the early days of digital signal processing hearing aids had quite long delays, and this prompted Brian Moore, one of the gurus of psychoacoustics, to find out what is the minimum, the maximum tolerable delay. And this wasn't an easy measurement, and he didn't come up with a very exact answer, but anything more than about 2.5 milliseconds produced obvious distortions to the sound. And most hearing aids at that stage had delays of about 7 or 8 milliseconds, and so they didn't sound very good. So we decided, well, let's try and do something about this. And the delay in our current hearing aids is about 1.5 milliseconds. So we managed to reduce that quite a lot. So there are actually usually 3 sounds, at least 3 sounds coming into the ear if a person is listening to their own voice. So in addition to the air-conducted sound and the amplified sound, there's also a bone-conducted sound from the larynx through the bones up to the ear. And if you put your fingers in your ears like this, what you're listening to is the bone-conducted sound, and it sounds quite different from the air-conducted sound from your own voice. And so this is one of the reasons why if you listen to your own voice in a recording, it sounds different from what you think it sounds when you're talking. But it also sounds quite different if you occlude the ear and put an earplug or an ear mould into the ear as well. So the mix of bone-conducted and air-conducted and amplified sound depends on the conditions of listening. Now, when you take copies of sounds and you add them together with a delay, if there's no delay, it just gets louder. If there's a short delay, then it starts to change the waveform and the spectrum. If there's quite a substantial delay, like about a couple of milliseconds or 4 or 5 milliseconds, then it starts to sound hollow and reverberant. And if there's a longer delay, then you hear an echo. And people using hearing aids report all of these things. And so by minimising the amount of delay, we reduce the number of adverse reports of sounds. The way we did that actually was by using a time domain signal path with an adaptive FIR filter in order to get the gain that we needed at each frequency, and we made it a minimum phase filter, so the taps were changed in phase as well as in amplitude in order to get the smallest group delay through the filter. One of the other essential technologies in hearing aids is feedback cancellation these days, and the way this works is that sound coming in comes out, gets fed back to the input, and gets bigger and bigger as it goes around this loop. So in hearing aids, this can produce all sorts of odd sorts of artifacts because the feedback path changes all the time. If you put your hand up close to the hearing aid, you introduce reflections off your hand back into the microphone. If you put a hat on, similar sorts of things happen. If you change one of the settings in the hearing aids, that can also change the amount of gain that you've got in the loop. And so people report chirps and screeches and ringing and all sorts of odd things.
Feedback suppression, or AFS, and AFSplus. Transient feedback occurs when conditions arise that initiate feedback. AFS quickly detects transient feedback and suppresses it within 1/10 of a second. When feedback oscillations are detected, a short-term gain reduction, or notch, is applied at the feedback frequency. The analysed frequencies, time length of operation, and gain reduction are all fully configurable. Dynamic Hearing's AFSplus system combines AFS with a slowly adapting feedback cancellation system, or FBC, to also address long-term feedback, which typically occurs for high gain settings or in open-ear fittings. The FBC component models the feedback signal and subtracts the modelled signal from the original hearing aid input. The system looks for similarities between the input and output signals and reduces or eliminates any similarities by subtraction. To maintain high sound quality, FBC operates in the higher frequencies where feedback is likely to occur. When it is in operation, the FBC component allows 15 to 18 dB more gain before feedback starts. This extends the fitting range of the hearing aid, allowing more people to benefit from an open fitting. A canceller that is set to respond too quickly can affect sound quality. Tonal sounds such as music and microwave beeps can easily trigger a feedback canceller, leading to artifacts in the sound. This is called entrainment. So the FBC component is set with a slow response time to ensure that it is only capturing real feedback situations. For this reason, in Dynamic Hearing's AFSplus system, the AFS and FBC component are configured to operate at different stages of feedback development. The AFS kicks in within 1/10 of a second if there is transient feedback. The FBC is set to respond slowly to avoid entrainment. This ensures sound quality is not compromised, as only long-term feedback is actually cancelled. So for instance, if a hat is put on which introduces feedback, the AFS will first suppress the feedback with a notch. The slower FBC then recognises that long-term feedback is present and cancels it. Gain reduced at the feedback frequency by the AFS slowly increases as the AFS backs off.
Okay, so over time we developed a more complete offering of sound processing algorithms for hearing aid companies around the world to use, and gained more and more customers. One of my favourite stories is about a German company called Interton, and they had about 4 or 5% of the European market, and they were using the same open platform chips that we had developed the sound processing for. So I took a bit of a risk and said to one of their chief engineers, lend me one of your hearing aids and I'll load our software into it, and then you can see what it sounds like. So before dinner he gave me a hearing aid, and I loaded the software into it, and I was very jet lagged, and unfortunately I fell asleep. So they came and woke me up, and I gave them back the hearing aid, and the next day one of the owners of the company, who was actually a machinist and liked to make hearing aid parts in his machine shop, said, "Oh, we need to give it the machine shop test." And he put it on and went into his machine shop to listen to his lathes and drills and things. And he came back and said, "Wow, they sound the way they used to sound." And so we ended up with $1 million license for the sound processing for Interton, and they continued to use it until they were bought out by GN Resound, and GN Resound went back to the old compression sounds. But Interton grew quite a lot in that time, and they sold the company for a lot more than they would have if they hadn't been using that sound processing. So digital signal processing in hearing aids, I think, is fantastic. It opens the door for a whole lot of things that just were not possible without digital technology. Just to show you finally what effect they have in terms of benefit, I want to give you some results from a few hundred people who've been using our hearing aids. So in a very early study, and other people have duplicated this, people have used a questionnaire called the Profile of Hearing Aid Performance to measure the percentage of problems that people have in everyday life in different environments with and without hearing aids. And this result here shows that for the upper line, the percentage of problems goes up quite steeply for people with an increasing hearing loss from about 20 decibels up to 100 decibels. Once you get to 100 dB, then people have problems all the time, 100% problems. But if you fit them with a hearing aid, that 100% problems goes down to about 30 or 35%. So this is a very noticeable improvement, and the improvement in quiet is greater the greater the hearing loss on this particular sort of test. Now we've got a bit more scientific than that, and these days Blamey and Saunders uses a word test. It's 50 words. If you're interested, you can do this online, and we'll tell you whether or not you've got a hearing loss when you get to the end of the test. But we also use this test for a number of other things. So in this case, we've had about 500 people do the test with hearing aids on and do the hearing aid test without hearing aids, or do the hearing test without hearing aids. And the difference between the aided and the unaided score, which is a word test out of 50, is shown by the red dots here. And if you fit a curve to that, you see that people's the amount of benefit increases up to the point where people have a hearing loss of about 50 dB. So hearing aids can help quite a lot for people with mild hearing losses. That's between 20 dB and above, but they give them a much bigger benefit for people with a greater hearing loss. And that's because they have more problems the greater the hearing loss. So there's more room, there's less of a ceiling effect, if you like. And then after the hearing loss begins to get greater than about 52 dB, then the benefit goes down. People no longer have enough hearing to benefit from the amplified sound. And if you draw a graph of the aided versus the unaided score and draw a regression line through that, you find that on average people are making about half as many errors in the aided condition as they did in the unaided condition on this very hard word test. If you do a similar thing with sentences, you find that on average people make about 1/4 as many errors for sentences in the aided condition as they did in the unaided condition. One of the reasons for doing this particular test in this way is that there's a lot of speculation in the literature about the effect of expectations, one way or the other, on people who come in to buy hearing aids. So what this is saying is you shouldn't expect to make no errors with your hearing aids on, but you should expect to make a lot fewer. And if you make 1/4 as many errors in running speech, that's a big improvement. You're saying what? Only 1/4 as much as you would have before. And people notice the difference. So this is a summary of the realistic expectations that I think people should have if they are looking at purchasing hearing aids. So in difficult situations, you can expect that you'll have about half as much difficulty, make half as many errors. In normal situations with running speech, you'll have about a quarter as many issues as you had before. If you're thinking about hearing loss, and not very many people do, but a person with a mild hearing loss can perform like a person with normal hearing. A person with a moderate hearing loss can perform like a person with a mild hearing loss. And a person with severe hearing loss begins to perform like a person with a moderate hearing loss. So that's my last slide, and thank you very much for your attention. I'd be happy to answer any questions if there are any.
I'll start the questions and then we'll take questions from the group. The bone conduction headphones are becoming popular, particularly with these people that are riding bicycles because they're not occluding their ear canals. Have you looked at that as an adjunct to hearing aid technologies?
No, we haven't, but there are hearing aids that are called bone conduction hearing aids that use only bone conduction and don't have an acoustic component as well. One of them is quite invasive. You need to have a bolt put in the side of your head, and that is stimulated cochlea make those. It's called the bone anchored hearing aid.
Okay, thanks. Just now taking questions. Certainly there's one there. Yes.
Fairly early in the talk, you showed us a photograph of a teacher in a classroom, and you had on the photo you had some lines labelled normal, mid and low. But the low line was only about twice the distance from the speaker's mouth as the normal one. So in free field that would only be 6 dB lower sound pressure level. In the reverberant space like that classroom it would be a lot less. But the big difference would be that the kiddie nearest the teacher would be in the direct sound field and the one at the back would be in the reverberant sound field. If you'd been using that slide to talk to us about the directional microphone, it would have meant a lot to me, but I didn't understand, given that the very small sound pressure level differences that picture depicted, what role it had in the part of the talk that you put it in.
Okay, so yes, those labels, normal, mid and low, referred to the sound levels that we used in our clinical trial. And there was about a 10 dB difference between the normal level and the low level. So the normal level was 65 dB SPL, the low level was 55. So your observation that there was a relatively small level difference was correct. That clinical trial was done with in the very early days before we had an adaptive directional microphone, so it was all done with omnidirectional microphones. Yeah.
Okay. Yes.
Thank you for the presentation. It was terrific. I'm interested in the spectral programming, the 64 channels. Would there be some spectral shift, spectral distortion introduced by analysing 64 channels independently, or is there linking between the channels to reduce spectral distortion?
So the channels are overlapping. They're not completely discrete or separate. And so the way we do it is a way that's been developed with a great deal of experimentation along the way. And I can honestly say that no, there's very little distortion. In order to avoid some artefacts, we do a little bit of smoothing, so we never have more than a 6 dB difference between one channel and the adjacent one. But when you get to higher frequencies, you can have 10 channels per octave or something like that, so it's not a big constraint.
Are you doing anything in relation to optimising the performance in relation to the actual hearing loss versus frequency?
Yes, we are. And I'm, if you'll have me, going to give a second talk about that specific thing. Usually when you go to an audiologist, they do an audiogram and they use that information to adjust the settings of the hearing aids. and in between the audiogram and the settings there's a thing called the hearing aid prescription. And there are 4 or 5 different types around the world developed by gurus like Harvey Dillon or Richard Seawald or what's his name, Moore, and they're quite different prescriptions, but they all swear black and blue that theirs is the best. Now, one of the things that I skipped over is that ADRO doesn't do that. ADRO uses a comfortable level, and in fitting the hearing aids we play sounds from the hearing aid themselves and get the user to adjust them to a comfortable level across frequency. And that loudness balancing procedure is very similar to what happens with cochlear implants, and so we get a good balance between a cochlear implant and a hearing aid, but we also get good compensation for sounds at a comfortable level, not at threshold level and with some arbitrary loudness growth function that people think is the best.
Jim again?
Thank you. I'm interested in our ability to localise, and interaural time differences are critical in that function. Wearing one rather than two would introduce timing differences.
Yes.
Do you normally recommend that people might wear two to get balanced?
Yes. Yes, we do. Yep. Nearly always.
Right.
I've got another question. There's a very large range of different hearing aid brands and types. How do you know what you're getting?
Good question. Most of the time I don't know how you know what you're getting.
It. And you've just said in that talk that one of the manufacturers discontinued the advanced processing and reverted back to the older gain control strategy. How do you know?
How do I know that he did
Well,
that?
how do you know?
Well,
When
yeah.
You're in the market to buy a hearing aid. How do you know what you're getting?
Well, you can test hearing aids if you've got sophisticated equipment to see what they're doing, but it doesn't really help very much. What if you really want to get the best result for yourself as an individual, you really need to try a few different ones and choose the one that you like the best.
Okay.
Don't get talked into buying the most expensive one because it costs more, therefore it must be better. That I don't think applies. One of the reasons for some hearing aids being much more expensive than others, and they can be as much as $14,000 for two, is that people have started to put Bluetooth and wireless technologies into them, and so you can connect them to your phone directly and get some benefit in that specific situation, as long as you don't mind the battery going flat in 4 hours instead of a week. So there's swings and roundabouts with all these things. There's no silver bullet that's going to fix everything in a hearing aid, and there are substantial differences between them, and it's worth shopping around a bit.
Yes, there's one there.
As it happens, just a couple of years ago, I got ReSound hearing aids, which you mentioned.
Mm-hmm.
So these will be without the ADRO in, I presume.
Yes.
A, can the ADRO be reinstalled by other than ReSound?
No.
And B, this business about compression for loud things, I don't notice compression particularly. I don't feel the sound's being squashed. And quite often I might hear there's something happens, very loud noise in the vicinity. It nearly makes me jump, it's coming through so loud. And things like that. So I'm not sure what I'm trying to say now.
So compression is, you can have different amounts of compression. Depending on what your hearing loss is like, you might have a lot of compression or a sort of moderate amount of compression, or very little. Now, prior to doing these studies with ADRO and it wasn't the only thing that resulted in this change. People started imposing a maximum compression ratio of about 3 and a minimum attack time of about 50 milliseconds. So the slower you make the attack time and the lower the compression ratio you use, the lower the amount of distortion that you get. And so that's probably why a sudden loud sound isn't compressed very much, and it's possibly why the compression ratio may not be the theoretical best compression ratio for your hearing loss. So some sounds will still be too loud and some will be too soft. Now, one of the things that ADRO does is it operates very slowly, but it does have a maximum output limit as well, so that it will cut off sudden sounds very quickly, and in general it's more comfortable than a compression scheme that has these slower acting, lower compression ratios. And as you saw, produces about 10% better speech perception scores.
Graham.
Peter, battery life.
Yep.
You say that the aid will operate for about a week in normal conditions. That's 24/7 operation.
Oh, about 12 to 16 hours a day for between 7 and 10 days usually.
Do you use rechargeable batteries or do you use the standard batteries?
At the moment we use zinc air batteries. Rechargeable batteries usually only have a life of about 15 to 20 hours. I don't particularly like rechargeable batteries because not only do they have a lower life, they after 400 charges or so you need a major repair of the hearing aid to replace them. So one of the things that Blamey Saunders is doing at the moment is developing a hearing aid with rechargeable battery modules, so that you can buy a module for, I'm not sure what it will cost, but say about $20, and replace it after it's had 400 charges. And you can also carry around a spare if you want to just change it quickly.
Are these batteries, are these readily available at any electronic store, or are they a special battery?
The zinc air batteries are available all over the place, and you can get them free from National Hearing if you're a pensioner. Sorry, not National Hearing, Australian Hearing. The rechargeable ones are not so easily available, but any audiologist will be able to sell you some. Yeah.
John.
It seems to me that the choice of sampling frequency is quite critical.
Yep.
Because one is at one end it's constrained by bandwidth, the other affects directly the latency of processing, because it takes you that much shorter or longer to get the requisite number of samples into the FIR matrix to pass it through. Can you indicate what process you go through to determine the sampling frequency?
Yes, so all of the hearing aids that we use at the moment use a 16 kilohertz sampling rate, and you're quite right. If you're going to do a Fourier transform, then there's a substantial delay while you accumulate the buffer of samples that you need, and that's one of the reasons why we use this separate analysis path and sound processing path to get a much lower delay. Yeah. So the parameters that are actually controlling the FIR filter are delayed, but the sound itself is not delayed through the filter.
I like the presentation of explaining what it sounds or looks like hearing loss, but is there a standard approach of accumulating or simulating a hearing loss, because we normally don't have a hearing loss?
Yes, there are a few different types of simulations. Usually just making sound softer is not a good simulation. You also need to introduce some fuzziness so a reduction in the frequency resolution as well. Yeah.
Does it simulate the cochlear, or does it just it's like a linear filter or something?
No, it's not a linear filter. You need to introduce some distortion as well to reduce the frequency selectivity. And there are different ways of doing it, but I'm not an expert on those sorts of things. So.
But it's a part of the standard?
Well, it's typically used for parents of children with hearing problems to try and explain to them why they need to do something about their child's hearing loss. And there's a very good paper by Renier Plomp in about 1970 or so, where he talks about an attenuation component and a distortion or a noise component in hearing loss. And these two things can apparently vary independently of one another. So if you're just using the audiogram, you haven't actually got a complete description of the hearing loss.
Part of that question was, are there any demonstrations available for what it sounds like, perhaps online? Is that
something like a real model that you can actually give a real audio and get an audio output that sounds?
Yeah, I'm not aware of any, but I'm sure you'll find one if you have if you look enough. Yeah.
Okay, there you go.
I was wondering, what's in terms of hardware, what's the difference between the aids and, let's say, a smartphone? I presume the CPU would be much more powerful in a smartphone. So could you actually wrap your algorithms in a mobile app and have sort of a cheap, accessible hearing aid for, let's say, underdeveloped countries? Or is there issues with the AD, the latency? Where would it work or would it not work?
Yeah, it would certainly work. Whether or not it would sound as good as a hearing aid, I don't really know. In fact, I think quite a lot of people have tried to do what you're suggesting. Nobody has produced something that is so much cheaper and so much better than a hearing aid that the hearing aid manufacturers have stopped doing what they're doing. But
it's possibly the difficulty of wearing two iPhones on your ears.
Affording two iPhones.
John, did you have another question?
A slightly frivolous introduction, but you mentioned the use of adaptive echo cancellation as part of the process to get extra gain, something I have experience with, but about 250,000 times higher frequency. But I'd be interested to know if you've developed any techniques to automatically cancel my single frequency tinnitus.
No, we haven't, is the first answer. Whether it's possible is I think, still an open question.
Hang on,
this is another question, isn't
it? That was a prelude.
Oh, right.
But it arises from damage to the cochlea. And do any of these processing techniques or foreseeable future deal with non-linear distortions in the ear rather than the linear ones which you're addressing, which are purely frequency in the frequency plane shifts and emphasis?
Yes, there's a technique called frequency compression, which takes high frequencies and moves them down to lower frequencies, and that's quite successful in treating high frequency hearing loss, which is very steep, where you just can't get enough amplification at the very high frequencies. When it's been tested in a thorough scientific way to see whether it improves speech perception, the evidence is still a little bit unclear. Yep.
Related question from me: the use of masking sound or tone to attempt to help tinnitus or hyperacuity sufferers, is that something that's included in hearing aids, or is that available, or has that been looked at?
It's available in some hearing aids. We haven't got it in our hearing aids at the moment. One of the most persuasive arguments about tinnitus and why hearing aids can help is that as the signal from the ear is reduced as you're losing your hearing, the brain automatically turns up the cognitive gain, if you like. And so what you're doing is taking a noisy signal and the brain is making it louder and to try to regain the hearing that you've lost. Now, when you start to wear a hearing aid, of course, the sounds that are reaching the brain are a bit stronger and more meaningful, and so the hope is that the brain will turn down the cognitive gain a bit. And it does seem to work in a lot of people, but it's not a universal cure for tinnitus, and there are lots of different sorts of tinnitus that may have an origin that's different from the one that I was describing. Yep.
Thank you. Jim?
Many of us have experienced the situation of noisy restaurants, cafes, the difficulty of hearing in those environments getting worse as we get older. Is that specifically related to a frequency loss?
I think it has to be, but I think that's not the full story. So I think there are other processing changes that take place at the level of the brainstem and the brain that can account for part of that difficulty.
Can that be influenced by hearing aids? Obviously the adaptive microphone is working in that area.
Yes, I think it can. So you can produce a better signal. It's easier to process, even though you might have reduced processing capability in the brain. There's a lot of literature at the moment about the association of hearing loss and cognitive processing and early onset dementia and those sorts of things. The correlations seem to be quite strong. There does seem to be a causative element to it. There's very little evidence, or at least a lot of controversy, about whether hearing aids slows down that process. So it's actually something that a lot of people are looking at around the world.
Well, Peter, that has been excellent for me, and I hope it's been excellent for you. Very informative and well covered too, to give us just a little bit of the technology. But thank you for me. I really would like to thank Peter, and I'd like you to thank him too for a very good presentation. Before you do, we do have an opportunity for him to cover another aspect of hearing aids that he did not cover tonight in any detail later in the year, and so if we encourage him now, he might come back. So thank you very much, Peter.
Thank you very much. Well, it's been a great pleasure to talk to you all, and thank you for the great questions.